Hi, my name is Grant McClure, and today I'll be presenting my work on the numerical modelling of drug-eluting stents in arterial tissue. This study focuses on using finite difference methods to simulate drug transport and analyse the effects of convection, diffusion and reaction processes. I will also discuss the numerical methods used, compare my results with existing literature and evaluate different numerical schemes. Cardiovascular diseases are one of the leading causes of death globally, and drug-eluting stents play a crucial role in preventing restenosis, where arteries re-narrow after procedure. Drug-eluting stents work by gradually releasing a drug into the arterial walls, reducing excessive tissue growth. However, optimising drug release is challenging, and understanding how the drug spreads to the tissue is a key to improving effectiveness. As you can see in figure 1 is a diagram of a drug-eluting stent. We can see the balloon and where the drug is going to get released. This project applies numerical modelling techniques to simulate drug transport through the stent and compare different numerical approaches to solving the governing equations. The aim of this study is to develop a numerical model to simulate drug release and transport in arterial tissue. To achieve this, I have 3 key objectives. 1. Develop 1D and 2D models using finite difference methods. 2. Analyse how convection, diffusion, reaction influence drug distribution. 3. Compare different numerical schemes in terms of stability, accuracy and computational efficiency. And for any stats, we're saying statistical significance is when p is less than 0.05 and I'm using a 95% confidence interval. So we can initially set the Stent up as a 1D array of cells. At the far left, where L2 is, this is where we initially put the drug into the array, what into the tissue would be in this sense. And over time, it will convect and diffuse along the length of the stent. We say the red part initially has a concentration of 1 and over time it will slowly diffuse and convect out. We can govern this convection and diffusion by the following equations. We have a time component, a convection component shown by the letter V in the partial C dy, and also a second order diffusion term as well as a reaction term, where we can say C is a concentration of the drug, phi is a magnitude of transferable velocity due to convection, D is the diffusion coefficient of the drug in the y direction, and K represents the drug absorption rate in the tissue. So let's look at the maths. For the time derivative term, I use the forward difference. For the convection term, I use the backwards difference, and for the diffusion term, I use the central difference. So if we sub in these discretized forms into the formula, we get this format, and then if you rearrange that for our next term, the CIT plus 1, we get this formula here. So now we have this, we now have the time matching formula, which allows us to compute the concentration at next time step iteratively. So let's solve that. So let's now run this model with these following parameters here. Notice we set the number of grid points to 100, our time step, and 1e to the minus 4, and our max runtime of 10 seconds. And I'm not really changing any of the hyperparameters dv and k here, which will affect the results. You can see it's quite a steady slope down. Okay, so let's reduce the number of grid points now. Now, as we reduce the number of grid points, you can see to 10, you can see that it's a lot more blocky. And that is introducing noticeable errors, you can see. No other hyperparameters were changed, yeah? So now that's reduced, it just shows the importance of spatial resolution when you're implementing these models. So you ideally want to run it with a high number of grid points. It shows important as a creation of the mesh. Similarly, if we look at reducing the time step size, you can see it yields a slightly similar result, but the smaller your time step, the more accurate the process is. As you're doing it, as numerical integration kind of works like that. The smaller your infinitesimal number of sizes of blocks, the better. So, as you can see here, no other hyperparameters were changed, but you're better reducing the model. Any higher than 10 to the minus 3 introduces errors and could oscillate or just explode. Okay, so let's complicate this a bit now, and we'll model it in 2 dimensions. Exactly the same process and the same finite difference approaches, but we just expand it into a z direction. All the transport mechanisms remain the same in terms of convection and diffusion, but we're just in 2 different spatial dimensions. All we do to make this different is we just add in that z component into our partial derivatives. Yeah, and all the other meanings are the same. Let's derive the time marching formula. Okay, so let's again look at the maths. We start off by using the forward difference method for time derivative, time partial, and backward difference for the convection partial, and the central difference for the second order diffusion partial derivative. And then sub in these discretized terms, you can get these results here. Again, you notice we're adding that J dimension in, which adds it into our set, higher dimensions, which make it into a 2D form. And then if you rearrange for the next term, we get this formula here, which we can then use to solve iteratively again in a time marching way. So let's look at this in a convection dominated scenario. So in convection dominated scenario, increase the velocity, transferring velocity term, and you can see here you've got rapid dispersion. The convection pushes the drug through the arterial tissue. Comparing this to the paper by McGinty, a similar trend is observed in the first few seconds where higher velocity enhances drug transport rate. We should also notice this CFL condition, which is 0 for basically all the simulations we're running. So we can kind of say that most of them are going to be stable. Let's do the same again. In contrast, when diffusion dominates, the drug spreads more gradually. This results in a smoother concentration gradient as the drug distributes from high concentration to low concentration areas. Compared to the paper by McGinty, increased diffusion shows a consistent pattern. It shows spatial uniformity of the drug transport. Again, the CFL condition is the same, and every other hyperparameter is the same. All their meshes the same size. Only thing we're changing is these values of dV and K. So finally, in a reaction dominated scenario, the drug absorption rate plays a significant role into the tissue. You can kind of see here, if we run the simulation, that it's very slow to run. You can see that there's a slight concentration difference, but here they've got quite a low diffusion term and a low velocity, which means you can kind of see it starting to the concentration starting to change at the border. But it's not going to make a significant difference. It just kind of shows how important it is. This slightly aligns with the McGinty paper, but they used an implicit method, which made a difference in how much effect this has. Obviously, tailoring with these hyperparameters dV and K would affect. They need more of a balance. So while I was editing this, I just wanted to add also it shows the importance of the need for convection and diffusion in these types of equations. So let's look at different methods for our 1D. So to explore this, I used a Lax-Wendroff method, which introduced a second order partial derivative term, which is slightly different from our old methods, but we're only changing the convection term. So here shows the new formula, which we're using for the next time step. So now if we run these simulations, we can see that they're both very similar to each other. They both look like visually kind of identical. But if we run a statistics test on it, so I used a paired t-test, but I used, then it wasn't normally distributed, so I used a Wilcoxon test, which is the non-parametric version of paired t, and I got a p-value of 0.038, which indicates a statistically significant difference. So what I did next was I did the same for two-dimensional methods, but again I just replaced the convection term. But I decided to use a second order backwards difference, which you can see here. So again, both methods I'm only replacing the convection term. Every other method we mentioned before is still the same. So let's run these simulations, and again, you probably couldn't really notice the difference. They both look very similar. But if we run another t-test on it, we get a p-value of 0, which indicates a statistically significant difference. That was using the final concentration terms. So, to conclude, I numerically modelled the drug transport in arterial tissue using finite difference methods. So our key takeaways include finite difference methods work well for simulating drug transport with different regimes, including drug distribution. If you use alternative schemes, improves accuracy and stability. The CFL condition does stay the same, but it seems adding more terms kind of makes it a bit more accurate as well. But you're increasing computational cost as well. Both the convection and diffusion dominated scenarios matched with the McGinty paper, and statistical tests confirm significant difference between the different numerical methods. Whether that's good or bad or worth the extra computational cost is to be argued. So to further improve, I would use an implicit scheme. The methods was a run in C, which makes a bit more difficult in terms of implementing an implicit method, as you have to implement a matrix solver. So I'd use higher order methods, again increasing computational cost, you could lose there's some data loss in there if you're starting from different steps. I'd also do it, since diffusion's anisotropic anyway, working in different directions, then you'd really want to model like real arterial properties, move into 3D, and I would use a different way of doing the CSV. As you probably realised in the code, that the data expansion can go quite fast, but that's why there's a few safety nets in the code as well. And then some references. Thank you.